Hey class, this is Mr. Roberts, and as promised, here's the Chapter 7 test corrections. Again, if you're interested in trying to recoup some of the points you missed on this test, go through and identify every single one of the questions where you missed some points. Go through and try and figure out exactly what you did wrong. I want you to copy down the question and the correct solution, and then also include a brief explanation of what it is that you did incorrectly. In addition, there is a small quiz that you will take. Stop by at lunchtime sometime, and we'll look at that. All right, so let's begin. So first question says, enough information is provided to prove that these triangles are congruent. A flowchart proof contains ovals with statements and justifications. Ovals are connected by arrows that show the relationship between ideas in your proof. Create a flowchart proof that explains why these triangles are congruent. So first thing, there's a couple things that are given in this diagram, and the first thing that is given is the fact that these lines are parallel to each other, and I've given you that in two ways, right? One of them is having these arrows on top of them, right? These indicate parallel, and also I wrote it. I said line AK is parallel to line BG. So that is going to be an important idea for this proof, because the fact that those lines are parallel to each other allows me to conclude that this angle, and if you look very closely, it goes from the parallel line, it jumps onto this transversal, goes along the transversal, jumps off the parallel, and then jumps off the transversal and gets onto the other parallel line. So those lines that I just marked in this orangish color are alternate interior angles. Alternate interior angles are not always congruent, but if they are connecting, or if they're the result of a transversal cutting parallel lines, they are. So that's why this parallel line business is important, and I'm going to write that first. I'm going to say that AK, line AK, is parallel, just these two vertical lines next to each other, to line BG, line BG, and that's given. It's given two ways. Now, because of that, because those are parallel lines, right, I can now get that a pair of alternate interior angles are congruent. And this is important because they're parts of these triangles. So I can say that angle AKG, angle A to K to G, is congruent to, let me see, BGK, B to G to K. Now, these are congruent angles because they are alternate interior angles with parallel lines. And I know you're saying, wait, what parallel lines? Well, see, that's the thing. The reason why we like to have this thing right here flowing into it is because, hey, that provides the parallel lines that we need. So we've got the parallel lines because of the oval above it. So again, we're including statements, things that we believe are true, and then justification for those statements off to the side. Some of these things need supporting information, and the parallel lines are supporting information for this particular statement. All right, let's move on. We didn't talk about why these are going to end up being congruent to each other, but it is because of I believe it's angle side angle. So if you let me mark these back in orange. So these we've got to be congruent to each other because they are alternate interior angles with the parallel lines. The other thing that's true is that this line right down the middle is a segment that's part of both triangles, and because it's the same segment, right, it's congruent to itself. That's the reflexive property. So I'm going to go ahead and include that. I'll say that segment GK is congruent to segment GK, and that's just the reflexive property. Things are congruent to themselves. They are also segments are also equal in length to themselves also. So there's a reflexive property for congruence and a reflexive property for equality. I'm fine with you just saying it's the reflexive property. And then the other thing that's here is we've got another pair of angles, and these angles were given to us. Angle G and angle K are poor names for these angles because I don't know what angle you're talking about. So let me show you, for example. So you could say angle G and it could be this blue one, right? You could say this largest angle. Or you could say angle G and maybe you mean this purple one. Or maybe you say G and you mean the little one that's in orange below. So when we have multiple angles hanging out in one vertex, it's really important that we use a name that specifies exactly which angle we're talking about. And we do that by using three vertices. So I could say, for example, angle AGK, A to G to K. So this is the convention, and this G right here is the vertex, which would be the name we'd naturally be using. But notice that it's kind of sandwiched in the middle. So I'm coming from A along the segment to G, and then from segment point G out along the segment to K. So that's the name of that angle. And then the other angle I could call BKG, angle B to K to G. But I forgot the angle symbol in there, and that's going to drive me crazy. So let me angle BKG, BK. G. There we go. Those are congruent to each other because it was given on the diagram, right? That's those little tick marks on those angles indicate they're given. So I have all kinds of things that are ready to support this triangle congruent statement, and I think I could make it now. I think I can say, for example, that triangle, let's do this. I'm going to start with G, then go to K, then go to A. So I'll say triangle G to K to A. Now that I've specified that, there's only one way I can say the other side. So I said G to K to A, going that way. So I think I have to go, what do I have to do? I have to go, I went G to K to A. So I'm going to have to go K to, wait a minute. I said G, K, A. Oh, I'm going to have to say K, KGB. Oh, that's clever. I'm going to have to say is congruent to angle K to G to B. Is that right? G to K to A and then K to G to B. That's right. Now, why are those triangles congruent? Well, they met one of our 5 triangle congruence conditions, right? In this case, the one that we have is we've got angle, side angle. So it's by angle, side angle that these are congruent. Now I make that and it's like, wait, where are the angle, side angles? Well, here's a pair of angles that are congruent, right? Here's the side that's congruent. It's by the reflexive property. And then my second pair of angles happen because of the parallel lines. So you can see not only am I including a statement and a reason like I would in a 2-column proof, but I'm also saying which pieces of information relate to each other. So this is a proof that these two triangles are congruent. It's a flowchart proof they're congruent by angle, side angle. Let's go on to question number 2. Question 2 says, simplify completely. Your answer may only contain positive exponents and also no giant ones, right? We can't leave any common factors laying around. So that's part of, I could probably write paragraphs on simplification, but we understand no giant ones and no negative exponents. And factors that can be combined are. So when I take a look at this, the first thing I notice is I do have this negative exponent. It's y to the negative second power. And it's awfully tempting when you see y to the negative second over y to the second to think that forms a giant 1, but it doesn't, right? Y to the negative second is not y to the second power. So we typically talk about destroying, that's aggressive, eliminating negative exponents by just multiplying it by the opposite. So you can see I'm taking y to the negative second and I'm multiplying that by y to the second power. When I do that, that becomes y to the 0 power, which equals 1. So my thinking is, hey, this is now y to the 0, which is 1. So that box that I just circled in orange, that equals the number 1. So it's not going to be part of my answer. It's just a 1. So let's write what we have now with that 1 taken care of. So now I have 3x squared in the numerator, and in my denominator I've got 9y to the 4th power now. So there's one more thing that we can do, right? Thinking about the 3 and the 9. 9, of course, is 3 times 3, so you can see that there is a giant 1 here. Be real careful. There's a 1 in that numerator and a 3 in the denominator, so this becomes 1/3. So my final answer is going to be x to the second power over 3 times y to the 4th power. X to the second over 3y to the fourth. Let's jump over and look at B. In question B, there's a couple giant ones that are lurking here, so we'll rewrite this so we can expose those. I'm going to write this numerator as 7 times x squared times x to the third. Now I haven't changed the numerator at all, right? If you look closely, this thing is exactly equal to x to the fifth, right? So there's no modification of it. The reason why I did that is I want to be able to very clearly see what is lurking below. So below there was an x squared, right? So now I can see the giant one that's forming with that. So this is going to create a product of 1. And the other thing is that 42 is going to be 6 times 7. So this is also going to produce a product of 1. So when I look at that, right, you can see now I'm left with x to the third power in the numerator, rather, x to the thirds in the numerator. And in the denominator, I have just the value 6. So this is my answer. It is x cubed over 6. Let's go down and look at part B. Whoops. For B, oh, that's nice. I'm going to do the same thing. I'm going to that I did in part A. I'm going to clean up and get rid of this negative exponent. So to do that, I'm going to multiply this by a to the second over a to the second. So the thinking, again, I keep saying this just to make it clear, right? I'm multiplying this original problem times the number 1. So I don't change its value. I'm just changing how it looks. In the denominator, when I multiply a to the negative second times a to the second, I end up creating the number 1 because that's a to the 0, and a to the 0 equals 1. So what I have now in the denominator, I have just the number 1, and in my numerator I've got 1, 2, and then 6, and then 7, 8, and then 8, and then 7 more factors. I've got 15 factors of a, so I've got a to the 15th power in my numerator. So the final answer then is just going to be a to the 15th power. This over 1 you could leave, but it's not necessary, right? All right, final question is D. On D, I'm gonna do the exact same thing that I keep doing, right? So I'm gonna multiply this times something to get rid of the negative exponent. The thing that I'm going to multiply it by in the numerator is going to be 3x squared to the positive first over 3x squared to the positive first. So again, I just created the number 1 in the numerator because I've got 3x squared in parentheses to the 0 power, which equals exactly the number 1. In my denominator, when I take this 3x squared and I raise it to this first power, this is just 3x squared. So my answer is 1 over 3 times x, or 3 times x squared. All right, let's move on to the second page, question number 3. Whoops, there we go. It says a geometric sequence is defined recursively. So this is a recursive definition. Recursive definitions always require 2 pieces of information, right? We need to know how to get to a future term. So this says in order to get to the next term, take the term that you're at and multiply it by 2. So that's how I read those recursive definitions. To get to a new term, take the term that you're at and multiply by 2. And then, by the way, the first term is 1/16. So it says next, go ahead and list the first 5 values of this sequence. So the very first value is, you can see right here, the very first value is 1/16. And now I'm just going to continue to double that. So if I take 1/16 and I multiply it by 2, I get 2 over 16, and I can reduce that to 1/8, right? And then if I take 1/8 and I double that, I get 2/8, which reduces to 1/4. If I double that, I get 2/4, which reduces to 1/2. And if I double that, I get the number 1, right? So I think that that's the first 5 terms: 1/16, 1/8, 1/4, 1/2, and then 1. Next it says, write the explicit equation for this sequence. Well, this is a geometric sequence, right? We know that this sequence is just limited to these precise values. We've been looking at exponential functions, which are related, right? The geometric sequence just has individual points. The domain is restricted to just the whole numbers, right? Or the ordinal numbers, 1, 2, 3, 4, 5. In the geometric equation, or the exponential equation, we don't have such a restriction. But Anyways, why am I saying this? I don't know. I'll just be quiet. So I do need to know the 0th term if I want to write the explicit equation. Remember, this is the recursive. I need the explicit equation. And in order to go back to the 0th term, you can see that if I go backwards, I'm doubling the denominator, right? So double the denominator goes from 2 to 4, 4 to 8, 8 to 16. So my 0th term would be 1 over 32. And I'm going to write this as, I guess I'll use t of n. T of n, well, I used a of n up above, so I'll use a of n is going to equal 1/32 times 2 raised to the nth power. So this is showing every single time I want to move forward in this sequence, right, I'm going to multiply by another number 2. And when I put in 1, right, I get 1/32 times 2, which gives me exactly 1/16. And from there, and then the last question here says find the 12th term of this sequence. Well, I'm not gonna do that manually, so let me grab my friend. Alpha, I'm gonna get a nice fraction though. So here's a fraction template, and I'm gonna have 1 over 32, and I'm going to multiply that times 2 raised to a power, and the power we're raising to is 12 because I want the 12th term in the sequence. And when I do it, I get 128. So a of 12, the 12th term in the sequence is 128. And just to check, I'm going to put 5 in there and make sure that it does give me 5 should give me the number 1. So if I come back up here and whoops, no, there it is, and I'm going to delete the 2. So you can see if I put in the n equals 5, I should get this value from the sequence, and I get wait a minute. Oh, that gives me the first term. Yeah, that's obviously correct. I was trying to get the 5th term. That means I need to put in the number 5. There it is, and I get 1. Beautiful. All right, so that's it for that question. Let's move on to number 4. It says the two triangles below are similar. The triangle on the left, that would be this one on the left one, is scaled to produce the triangle on the right. So you can see the direction of this scaling. We're starting, this is the original one, and this is the direction to get to the new shape. So you know that when we multiply the original times the scale factor, it gives us the new value. So our scale factor should be a value less than 1 because I can see it's reducing the size of it. So if I want to figure out the scale factor, I'm just going to identify a spot where I've got two numbers that are the same. And you can see here's 14, and on the same side I've got a 21, right? So these I'm just inferring that these are the sides that go to each other. If that's wrong, the person who wrote this problem is incredibly cruel. But I think we're good. So I'm going to take 14, that's the new dimension, and divide it by the original. This reduces, both of those can be divided by 7, and I would get 2 over 3, 2/3, right? So the scale factor should be 2/3. So if I take one of the dimension, and by the way, the scale factors, its units are inches. It's 2 inches over 3 inches, and when you've got inches over inches, that just equals the number 1. So this is the scale factor actually has no units, right? It's just 2/3. And again, if I take a number like 21 and I multiply that times the scale factor, which is 2 divided by 3, I get exactly the 14, right? So multiplying by the scale factor, it lets me move from the larger triangle to the smaller one. Now the next thing is figure out what x is. Well, this is not going to be difficult because I can see that x is exactly, it's lining up with this side that's 12, right? So if I look at this, I'm going to take the 12, multiply it by my scale factor, and then I should get what x is. So x should equal my 12, x should equal 12 times the scale factor of 2/3. Well, 12 divided by 3 is 4, and 4 times 2 is 8, so this should be 8. So x should be 8. Now this does have units, right? These are inches. I didn't take inches divided by inches, so this dimension is 8. And then the other one, the last dimension up here, you can see I've got this 6 and I've got this 6. Well, I'm supposed to take y and multiply it by 2/3 in order to get 6. And to organize my thinking, I could do that. I could say y times 2/3 would give me 6. Well, if I want to solve that equation for y, I could multiply both sides by 3, divide by 2, or I could just simply take both sides and multiply by 3/2. Think about it. If you multiply by 3 and then divide by 2, you're multiplying by 3/2. So both sides times 3/2 is going to give me 3/2 times 6. Half of 6 is 3. 3 times 3 is 9. This should be 9 inches. So that is the dimension of y. Moving on to question 5. There's two equations here to solve. One of them is kind of a fraction buster, and the other one's perhaps looking inside. So let's think about this one first. So the error that I saw a lot was many of you looked at this and said, hey, let me multiply everything by 6. And you did that, except you lied. Perhaps many of you did. You told a little fib. If I was to multiply all these by 6, I would get 6 divided by 2 is 3, right? 6 divided by 2 is 3 times 9 is, I would get 18. And then many of you just wrote an x in the numerator. You forgot the x was down below, right? So if you're doing that, it's 18 over x. This x is still living in the denominator, right? So again, the thinking is I'm multiplying every single one of these times a 6 in the numerator. So I've done it, so I'm going to erase that. So every single one of those terms got a factor of 6, and then when I clean it up, most of the fractions go away. So I've got 18 over x, and then 6 divided by 3 is 2 plus 14, and then that equals 6 divided by 2 is 3. That would be 21. So the thing is where is x? X is in your denominator, and you got an answer that was the reciprocal of the correct answer. So if I want to get the answer now, I'm going to multiply everything by x because I want to get x out of the denominator. If I do that, when I multiply this term by x, I'm going to get just the number 18, and then I'm going to have an x here and an x here. So when all of those are multiplied by x, we end up with 18 plus or 14x equals 21x, correct? And then if I subtract, what am I going to subtract? 14x from both sides, I get that 18 is 7x. And then if I divide both sides by 7, I get 18/7 is what x is. So that was the problem. Although as I look at this answer right now, it seems like I've made a mistake somewhere, and I can't for the life of me. I know I've made a mistake, but I can't exactly see where it's at. 6 divided by 2 is 3. Many of you have been watching this for a while, like, is he ever going to notice? Yeah, 6, whoops, go away. 6 divided by 2 is 3, and 3 times 9 is, this should be 27. Oh my gosh. Oh my gosh. Now, I would, and I did when I created my answer key, plug that number in, and that's not the number I got the first time. So I'm looking at my answer key, I'm like, what did I do? If I would have plugged that in, I would have caught that. But yeah, no excuses, right? It happens, right? That's why we plug these things in, because when we plug them in, we can figure out, wait a minute, that's why there's a mistake there, because the value you got, Mr. Roberts, 18/7 doesn't work. But you claim without proof that 27/7 will. Oh, well, let me give you that proof. So let's see if I can do this here. I'll turn on the calculator. I'm going to enter it. It is a nice, cozy little oh, my goodness, I don't want that. Second, quit. I'm going to hit alpha, and I'm going to grab the fraction template. I've got a numerator of 27, and I've got a denominator of 7. So this is what I claim my answer is. So I'm going to just go ahead and look at the original equation. So that's going to be 9 divided by, and then I'll throw parentheses around this, 2 times my value of x. Where is it at? There it is. Gotcha. Close parentheses, right? And then plus, and I need another fraction. Oh dear, another fraction. Come on, fraction. And in that fraction, I'm going to do 7 over 3. And when I press enter, I should get 7/2. Oh, and I do. So Yes, when you plug, and you can't see the original equation because I messed it all up, but when you plug right here, when you plug 27/7 into that, both sides of this become 7/2 on the left hand side, and the right hand side already is 7/2. So that is the solution. Let's move on to B. So B, I know the overgeneralizing that happened, right? I think many of you saw this and said, hey, to deal with this square root, I'm just going to square both sides. And when you did, you incorrectly squared the left-hand side. So if you wanted to go that way, I just want you to understand that means that you have to square that. And when you look at that, that's crazy looking. That's actually a binomial. And when you want to square that binomial, right, you would need an area model to talk about that. So one of the dimensions would be the square root of 3x plus 12, and then it's a -6, and you'd have another 3x plus 12, and you'd have a -6 down here. And you could find all four of these and attempt to simplify it. I don't think that's a great way to go, right? Much better thing to do, because we can do it simply, is just add 6 to both sides. So if I do that, on the left hand side now, I now have the square root of 3x plus 12. And on the right hand side, I've got the value 16. Fabulous. So I know that this expression inside, it has to be the square of 16. It has to be 16 squared. And I know I went to college, but I do not know what it's 2 something, right? 256. Isn't that what it is? Oh no, now that's going to be a lot bigger. It is 256. Yeah, okay, that's embarrassing. So, because I should know that, right? That's one of the things you learn in college is all your squares. No, it's not. So this is going to be 3x plus 12, and over here, I need that thing to be the number 256. So just looking inside, that purple box must be the number 256, so I'm forcing it to be. I'm setting it equal to 256 and solving. So that means that 3x is going to equal, let's take away 12. That's going to be 244. Yes. And then to get x alone, I'm just going to divide. So that's going to be 244 divided by 3. And honestly, that's a fine answer. I don't have a problem with that. You know, this is an easy answer to check, because if you look at it, if I put that x in right there, right, 244 over 3, I'm going to immediately multiply it by 3, which makes it the number 244. And then, right, so I've got 244, and then I'm going to add 12 to that. So I'm going to say plus the number 12, right, and then I'm going to press enter, and I get this number, and I need to take the square root of that. So I'm going to say second square root of 256, and then after I take the square root of that, I need to subtract 6, and when I do, I get 10. Perfect, right? So x is 243 over 3. All right, I think we're moving on to our second to the last page. So there's a lot of parts here, right? It says use the polygon at right to answer parts A through E. First part A, it says find the equation of the line that goes through HC. So here it is, and there's two things I know about it. So we're going to do, I'll color code this with we'll do yellow for part A. So I'm trying to find the equation of the line that goes through there. I can definitely grab the ruler, and I can grab this line, and I don't know if a white line would be smart, because, well, I'll just put that in there anyway. So I'm trying to find the equation of this line first. And as I do that, one of the things I notice is I can see it really clearly, the slope of that line, right? This has a y increase of 1 and a run of 1, 2, 3, 4. So I know the slope of HC is 1/4. So I'm just going to add that, right? Slope is equal to 1/4. And the other thing I've got is two different points, and it doesn't matter which one I use. H is apparently at 2, 3. So point H is where x is 2 and y is 3. If I look at it closely, x is 2 and y is 3, so that's point H. So I can use that point and the slope to find the equation of this line. So I'm just going to go ahead and plug things into y equals mx plus b. My y value is the 3, so I've got 3 equals my slope 1/4 times x, which is 2, and then plus b. So 1/4 times 2 is a half, so I've got 3 equals 1/2 plus b. That means that 3 minus 1/2 is b, and that means it's what? It's 2.5. Or I could do it this way. 3 is 6/2. Let me go up here. So this is 6/2 minus 1/2, which is 5/2. So b is 5/2. So I would write the equation of the line here as y is equal to 1/4 times x plus 5/2. Fabulous. That is the equation of that line. Now to check it, right, if you wanted to, when I plug in 2, it better give me 3, and I think it will, but also when I plug in 6, I should get 4 out of that. And you know what, even without going with the fraction template, it might be worth it to just do that. So if I hit 6 divided by 4, so that's 1/4 of x plus 5. Oh, of course this is going to work. 5 divided by 2. I can see that now even without a calculator. I get 4, yeah. So definitely that's the equation of line HC. Next it says find the equation of the line that goes through AI. Okay. So AI, oh, that line's actually already shown, isn't it? I'll just put a purple dot here. So this is A, and then I've got the I down below here. And the slope of that is up, what, 1, 2, 3, 4 over 1, 2, 3. So the slope is 4/3. So that's nice. I can get the slope from the graph. Equals 4/3. And then I guess I'll use this bottom point, which is at 2, 6, right? That was point I. Was it I? Yeah, that was I. Point I is at 2, 6. And you know what? I'm going to use the thing that I've mentioned this. I think it's on the window in the classroom, the point slope form. So remember, this is another way you can get the equation line. Y minus a y value that you know equals the slope times the quantity of x minus the x value that you know. So you can see I'm using subscripts here. Y sub 1 and x sub 1 are referring to this y value, this xy value that I know, right? So if I could just write everything down without solving for b, I'll manipulate it then, but this is kind of slick actually. So I can write y minus 6 equals my slope, which is 4/3 times x minus 2. Now that's not in slope-intercept form, which I may want, especially later on when I have to solve this system. So I would manipulate this a little bit. To manipulate it, I might distribute the 4/3, right? So I would say that this is 4/3 x, and then that would be a minus 8/3, right? Minus 8/3. And if I added 6 to both sides at the same time, right, I now know what y is. Y is equal to 4/3 x minus 8/3 plus 6. 6 I can write down as, what is that in terms of thirds? Is it 18/3? 18 divided by 3 is 6. Yeah, so that's the same as 6, so that's still plus 6. Why I did that is now I can combine those fractions. So my answer should be y is equal to 4/3 times x, and then plus 10/3. Oh, I did not leave a lot of room in there. Let me see if I can. Oh, no, I don't want a keyboard. Can I come in here and get this? Well, I'll make it small. I'll just leave it there. And this 3 is in the wrong spot now anyways. Okay, so this is my answer. This is my second equation. This is the equation line that goes through AI. Moving along. And by the way, let's go to part C. It says find the perimeter of the polygon. Assume that each linear unit is a centimeter. So I need to find the perimeter. And
Man, if you were using a pencil, it'd be nice because you could clean up some of these markings from the other problem. If you were doing it in pen, you know. Anyways, I'll clean this up so I can think about this. So if I'm going to write down the perimeter, a lot of these are easy to find. So I guess I'll do the perimeter in this blue. This is 1 unit. Oh, that's hardly seeable. Let me do this in red. And then from B to C, I can see that B has an X value or Y value at 10, and C has a Y value of 4. So this should be 6 units, and I can count it also, right? It's 1, 2, 3, 4, 5, 6. This is 2 units. That's 1 unit. This is 2 units. This is 3 units. And then the other pieces that I need to kind of consider are these two. Whoops. Let me highlight this with a different color. This one and this one and this one are congruent to each other. They have that same pattern. So that'll be nice. We can figure that out. And then also this one, right? It's a little bit different than the one below, obviously, so I'll use a different color. So let's think about these down here. This is a 1 by 2, right? It's up 1 over 2. This is over 1 down. This is over 2 down 2. They have different slopes, right? Not opposite reciprocal slopes, just slopes that are 2 over 2 over. That one has a slope of -2, and one has a slope of rise, 1/2. Quit talking, Roberts, just do the math. Okay, this is a right triangle, and this is a 1, and this is a 2. Clearly a 1 and a 2. So the area of I'm sorry, the length of that is this hypotenuse. So I'm looking at 1 squared plus 2 squared, which is 1 plus 4, which is equal to 5. So the area of this is this, the length of that rather, is the square root of 5. This is also the square root of 5. And then for this one, I've got a 1, 2, 3, 4, and a 1. Oh, that's beautiful. This is a 4 and a 3. This is a Pythagorean triple. 4 squared is 16. 3 squared is 9. 16 plus 9 is 25. And the square root of 25 is the length of that segment. So segment AI is 5 units long. So this is 5. So now I think I can kind of come through and figure out the area of this. So maybe I can keep track of this. Maybe I can't. Let me circle the ones that I've used in green. So 2, 4, this would be 6, and then that would be 12, and then 17, 18, 19, 20. Uh-oh, what? I feel like I'm missing something. 1, 2, 3, 4, 5, 6, 12, 13, 14, 15, 16, 17, 18, 19, 20. That's 20. Okay, so this, all of those are 20, and I write down 12 as I say 20. All of those are 20, but then I have plus a square root of 5 and plus another square root of 5. I've got 2 of those. And just to help you think about this, when you see that you're adding the same thing twice, like for example, if I had an x plus an x, and let me write an x twice, that's the same as 2 times x, right? Like 3 plus 3 is the same as 2 times 3, that's 6. So if I've got a root 5 plus another root 5, I can write that as 20 plus 2 times the square root of 5. So the answer for the perimeter of that thing is going to be 20 plus 2 root 5. And we are now on to the point about the midpoint. The midpoint. It says if H is the midpoint of segment BK, find the location of point K. Okay, so when I look at this, there's no K on the diagram, right? K is nowhere to be seen at all, but I'm told if H is the midpoint, so if this is in the middle of things, right, find the location of point K so that BK, right? So if you can see, here's the B. I have to come through here. I have to come through here and hit H, and then if I continue this for another like certain distance, right, eventually somewhere on this line, I'm going to find way over here in the other column where K is at. So I got to figure out where K is. So, you know, if I look at this, I could just count the points, right? When I go from B has a, it's a y value of 10, right? B is at 10. And when I come down here to h, this is at 3. So you can see I've got to go down 7 units. I got to go down 7 units, and then I got to go back 1, 2, 3, 4 units this way. So if I want to get this, I just need to start at h, and I need to go down 7 units and then back 4 units. So this is not hard, right? Well, maybe. So because 3 minus 7, so I got it. I'm at h right here. The y value is at 3, and I got to go down 7. 3 minus 7 is negative 4. So I know that my y value, the y is going to be at 3 minus 7, which is equal to negative 4. And then the x was at 2, right? X is at 2, but I need to go back 4. So 2 minus 4 would give me negative 2, right? 2 minus 4 is negative 2. So the x value should be at negative 2. That means that the location of k, point k, should be at the spot where x is negative 2 and y is negative 4. So negative 2, negative 4 is the location of k. Whew. I said, as you guys came in, I said, boy, this question, right, question 6 is the one that's going to consume your time. All right, so let's finish it off, right? Last part of this question, this crazy question, it says, check your answer to parts A and B. We already did that. Then solve the system of equation formed by using both equations. Give the location xy of the point where lines HC and AI meet. Write your answer below. So if you're looking at the original drawing we had for HC and here's AI, right? They're clearly meeting somewhere over in here. So this problem is asking us to figure out where they meet. Well, if I look at these two problems, right, one of them said y is equal to 1/4 x plus 5/2, and that was line HC. And the other one was y is equal to 4/3 x plus 10/3, and that's line AI. Well, this is clearly one of the best setups for the equal values method of solving a system, right? Clearly, within the context of this problem, y is equal to itself, and I've got two ways to express y, this way on the left and this way over here on the right. So I'm going to write the left one over here, 1/4 times x plus 5/2 is the same as 4/3 x plus 10/3. So what I'm looking for, this is going to give me the value of x once I solve it, and then I've got two equations above that'll help me figure out what y is. So if I look at my denominators, right, you can see I've got a 4, a 2, a 3, and another 3. So I don't have to multiply by 2 3's, and I don't have to multiply both the 4 and the 2 because 4 contains a factor of 2. So I think I just need to multiply by 12. If I multiply both sides of this by 12, I will have exactly none, 0 fractions. So that's definitely worth it to me. So I'm gonna put a factor of 12 across the whole thing. Actually, you know what? I'm gonna talk through this. So 12 times 1/4 is 3. So this is going to become 3x. 12 divided by 2 is 6 times 5 is this going to become plus 30. 12 divided by 3 is 4. Times 4 is 16x, and then 12 divided by 3 is 4. This is going to become positive 40. So let's take away, oh geez, no good choices here. I'll take away 3x from both sides, so it's going to give me negative 13x. And then I'm going to take away 40 from both sides. That's going to give me negative 10. Right? Did I do that right? Negative 10. Yeah, I don't know why I went that direction. Seems like I should have went the other way. Oh, no, that's not. 16x minus 3x is positive 13x. What am I talking about? Maybe it's time for a nap. 16 minus 3, yeah, is 16 minus 3 is 13x. That's correct. And 30 minus 40 is 10. Boy, I could sit here and do, you know what? I know that's right now, but you know what? if I'm being that dysfunctional, I should probably just, okay, so that's 30 is equal to 13x plus 40. And then if I take away 40 from each side, right, 30 minus 40 is negative 10. And over here I've got 13x. And to get x alone, I'm just going to take, it's negative 10 divided by 13. So there's the value of x. Whew. And now I need to get the value of y. And it doesn't matter which expression I use, both of these give me y, so I'll just use this one. So it says take 1/4 times this beautiful value. It's negative 10/13 for crying out loud. That's beautiful. And then plus 5/2. So let me grab this calculator because I'm fearful. Watch this. I'm going to do it without the fraction key, and then I'm going to force it to look like a fraction. So I'm going to go 1 divided by 4 times, and then if I need the negative, I got to use this button down below here, right? So I'm hitting negative 10 divided by 13, yeah, and then plus 5 divided by 2. Now, because I understand how this order of operation works, right, it's doing this multiplication division from left to right. This is not seen as a subtraction. That's why we need to use this opposite of 10. So this is 1/4 times negative 10/3 and then adding 5/2. And when I do that, it gives me this decimal for y. I could write that down, but I can also say just go math and then frac. And when I do that, it says 30/13. So there we go. So y is 30/13. So my solution is negative 10/13, comma 30/13. All right, that's that problem. Last page. That's the location where those. By the way, if I was to plug negative 10/13 in to both of those equations, they would both produce 30/13. So they're over at negative 10/13 and 30/13. What is 30/13? 30/13 is like, it's a little bit more than 2, right? It's a little bit more than 2. So they're meeting somewhere a little bit more than 2, but a negative x. So that looks reasonable. All right, last problems. Number 7. It says multiply each set of polynomials. You may want to use an area model to organize your work. Hey, if you're at a point where you're consistently doing this, especially binomial times a binomial, you don't have to use an area model. I'm just showing it just to remind us of what it looks like and why it might be useful, especially if we've got more than binomials. So along this dimension, I'll say this is 3 times a long. The length of that's 3a. The length of this is 2, so this is a generic area model. Up here, this is a units long, and then down here, this is negative 4. You cannot have that as a dimension of an actual rectangle, but it's a generic area model. A times 3a is 3a squared. 2 times a is 2a. Negative 4 times 3a would be negative 12a, and then finally negative 4 times 2 is negative 8. So you look at all the pieces here, and my answer should be 3 times a squared. Then I've got a negative 12a plus 2a, which would give me negative 10a, and then finally I've got the negative 8. So the one thing that's kind of tricky is that we've got this binomial that I have to square. Right, and then the next one, pretty common error, and I see this a lot, and I know what this is related to. If you had, for example, 3a and that was getting squared, you know that the answer to that is it's 9a squared, right? Because what is that? That's a 3a times another 3a. So there's a 3 times 3, which is the 9, and an a times a, which is the a squared. So what happens is you look at that, and many of you are overgeneralizing this and saying, hey, I'm squaring 2b, which is going to be 4b squared, and I'm squaring negative 1, which is plus 1. The problem with that is that that's not what you get when you square this binomial, right? To square a binomial means to multiply it exactly, right, by itself. Actually, to square anything means to multiply it by itself. If you look right here, if I wanted to square 3a squared, what did I do? I multiplied 3a times 3a. if I want to square 2b minus 1, I'm multiplying a 2b minus 1 times another 2b minus 1. That's why it might be useful, right, to slow down and just use an area model here. Actually, at this point, you may not need that. But I've got a length that's 2b and a negative 1, and I've got a 2b and a negative 1, and they're exactly the same. This is going to be 4 times b squared. That's a 2b, 2b. 2 times 2 is 4. b times b is b squared. This is going to be a minus 2b, another minus 2b, and this is going to be plus 1. So the product is 4b squared and then minus 4b and then plus 1. So if your answer that you got is missing this, what it means is that you're overgeneralizing. You think that multiplying squaring different terms is the same thing as squaring this binomial, and while squaring certainly is the same, right? The fundamental is to square something, you multiply it by itself, right? Well, do that over here. Multiply this thing times itself, and when you do that, you get this middle term, the minus 4b. So the correct product is 4b squared minus 4b and then plus 1. And then the last problem, I have a little trinomial here times the binomial, so I will definitely probably always use an area model in this case. So across the top, I've got a part that's 2a squared long, followed by a 3a, followed by a negative 1, and then down on this side there's an a and a 6. So there's 6 things that are going to go into this product, and many of them will be like terms, I suspect, and we can combine those. So up here, this is going to be an a times a 2a squared, a times 2a squared, which would be 2a cubed, right? A times a squared is a cubed. And then I've got an a again. See, these are all a. These I could color code that. This and this and this, those are all a units long. And then down below, like this is 6 units long, 6 units long, 6 units long. And then the other ones are changing a bit, right? These are all 2a squared long. Oh, this is so much fun. And this is 3a, and that's 3a, and that's 3a. And then I just realized I just ran out of colors. I don't have another color. So I'll just grab this red pen, and like this is like a negative 1, a negative 1, a negative 1. Totally not necessary, but it was just fun. This again, a times 3a is 3a squared. A times negative 1 is a negative a. 6 times a squared is 12a squared. 6 times 3a is 18a. And then 6 times negative 1 is negative 6. So where are my like terms? They are here. They are here. I have like terms, right? On these diagonals. These are like terms, so I can combine those. And these are like terms, so I combine those. So my product, my final answer for the last problem, the entire test, is going to be 2 times a cubed. And if I combine 12a squared and 3a squared, that's going to be plus 15a squared. And when I combine 18a and a negative a, that's going to be plus 17a, and then finally a minus 6. So let's read that again. It's 3a cubed plus 15a squared plus 17a minus 6. Well, that's it. I hope you found this helpful. I look forward to seeing you in class.